Heat treatment makes possible the use of steel for a wide variety of modern industrial purposes. In the heat treating shop, specific qualities are imparted to metal parts. They can be made harder, tougher, softer, given whatever special properties are needed during their manufacture or in their eventual performance. Steel may be hardened by heating it to a high temperature, high enough to make it red hot, and cooling it rapidly. Each job, each steel, has its own specifications. To take a typical case, these gun parts, called front guides, must be hard and tough to meet rigid performance demands. Heat treatment will impart the hardness required. But how hard are they now? The Rockwell hardness testing machine is an accurate means of finding relative hardness. The C scale of this Rockwell dial shows a reading of 10 to 11. The part under test isn't very hard. The specifications call for hardening it to Rockwell C 50 to 55. These front guides are taken to the hardening furnace. Here begins the process which will bring about the desired final hardness and toughness. The guides are now the responsibility of the heat treater, who will see the job through. The furnace is charged with the parts and heated. On this instrument, called a pyrometer, the heat treater can read the temperature in the furnace. When the proper temperature is reached, 1500 degrees Fahrenheit in this case, the parts are removed from the furnace. They are quenched, cooled rapidly in water. Heating and quenching together produce desired changes in the properties of the steel. After quenching, the heat treater again makes a Rockwell hardness test. The test reveals that the part has been hardened to about Rockwell C 62, 7 above the hardness called for. It has purposely been hardened to a point above specifications. Tempering, a toughening process, will bring the steel down to the exact required hardness. But our first problem is to know what accounts for the hardness of steel. In the heat treating process, the structure of the steel changes, and these changes govern its hardness. If we study steel under a microscope, we can observe its structure. Here is a picture of a steel photographed through a microscope. This micrograph shows the steel structure before hardening. This is an S.A.E. 1043 steel. S.A.E. means that the specifications of this steel are those of the Society of Automotive Engineers. 1043 is a numerical designation for this particular steel. It is a plain carbon steel containing 0.43% carbon by weight, a medium carbon content. This steel before heat treatment has a Rockwell C hardness of 10. Steel is composed of iron and carbon. In this micrograph, the lighter areas are called ferrite. Ferrite is iron. It contains an extremely small amount of carbon in solid solution, never more than 1/20%. The darker areas are called pearlite because of the lustrous mother-of-pearl appearance they sometimes present under the microscope. Pearlite contains practically all of the carbon present in the steel. Here's a micrograph showing well-defined pearlite. Pearlite is made up of alternate light layers of ferrite and dark layers of iron carbide. It is in the iron carbide layers that the carbon occurs. Ferrite and pearlite are both relatively soft. Under heat treatment, they both can be transformed into a new, hard substance. On this table we shall record at progressive hardening stages the quenching temperature, the structural changes, and the Rockwell C hardness. We have seen that in its untreated condition, the structure of this steel consists of pearlite, graphically indicated here by light and dark layers, and ferrite, indicated by a white area. We also know that the steel's Rockwell C hardness is 10. Now assume that the steel is heated in a furnace to, say, 1,000 degrees Fahrenheit and quenched in water. A micrograph of the steel at that stage shows that no structural change has taken place. So we record that when quenched from 1,000 degrees, the structure remains unchanged. A Rockwell C test would show that the hardness remains at 10. In fact, no change occurs until the steel is heated to 1,320 degrees and quenched. Now small changes have taken place in the pearlite areas. In this micrograph, we can see that new areas, light gray in shade, have formed. What happened? Here is a graphic representation of the steel in its original condition. This represents its pearlite area, and this its ferrite area. When the steel attained a temperature of 1,320 degrees, some of the pearlite formed a new crystal structure, austenite. Austenite is a solid solution of carbon in iron. It is, however, a transitional substance. When the steel was quenched, the austenite, in rapid cooling, transformed to still another new substance, martensite. The new light gray areas which appear in the micrograph are the martensite. Martensite is a very hard substance. Even the small amount now present in the steel is immeasurably harder. Its Rockwell C hardness is up to 19. Now let's heat the steel to 1,340 degrees. When quenched from this temperature, most of the pearlite changes to martensite. The original ferrite is still present. So the martensite area has increased. The additional martensite accounts for a rise in the steel's hardness, which is now 27. What happens if the steel is brought up to, say, 1,380 degrees and quenched? Now all the pearlite has transformed to martensite. In addition, some of the ferrite has also changed to martensite. So, when quenched from 1,380 degrees, the steel is composed of martensite and ferrite, a structure which gives a strikingly increased hardness, 51. When the steel is heated to 1,425 degrees and quenched, the micrograph shows that the structure has become almost all martensite. Only a little of the original ferrite is left. With its structure almost entirely martensitic, the steel is close to its maximum hardness. It is now 58. When the steel is heated to 1,450 degrees and quenched, a wholly martensitic structure is achieved. This structure gives the highest hardness obtainable in this steel by this kind of heat treatment. Quenched from 1,450 degrees, its structure all martensite, the steel's hardness is 60. This completes our record of the S.A.E. 1043 steel. Here is the point of initial hardening, 1320 degrees. This is called the lower critical temperature, the quenching temperature below which this steel will not harden. It was marked by the first appearance of martensite in the structure of the steel. Here is the point of maximum hardness, 1450 degrees. This is called the upper critical temperature of the steel. It was reached when the steel became entirely martensitic. Let's see what happens to a plain carbon steel of low carbon content under similar treatment. Here are a series of micrographs of such a steel at progressive stages of heat treatment. This is an S.A.E. 1013 steel. Its carbon content is 0.13%. This steel structure before hardening resembles that of the 1043 steel. It likewise consists of perlite and ferrite. But being a lower carbon steel, it has less perlite, the carbon-bearing constituent. Its Rockwell C hardness is 9. The first structural change in this steel takes place when it is heated to 1320 degrees and quenched. At this stage, some of the perlite has formed martensite. Its hardness is 17. When quenched from 1365 degrees, all the perlite has disappeared, and it is composed of martensite and ferrite. Its hardness is 29. After quenching from 1525 degrees, there is more martensite, but still a substantial amount of ferrite. Its hardness is now 38. Not until it is quenched from 1575 degrees do we get a micrograph that reveals a structure entirely martensitic. The Rockwell C reading is 45. The steel's maximum hardness. Now we can record the changes in the 1013 steel, as it was quenched from increasingly higher temperatures. These are the Rockwell C values at the various stages. This column shows graphically the steel structure at each stage. The pattern of the change in structure is similar to that for the 1043 steel. The hardness of the 1013 steel increased with the increase in martensite, as did the hardness of the 1043 steel. Here is the point of initial hardening in the 1013 steel. 1320 degrees Fahrenheit is its lower critical temperature, just as it was for the 1043 steel. Here is the point of maximum hardness for the 1013 steel. 1575 degrees is its upper critical temperature. This is considerably higher than the upper critical temperature of the 1043 steel, which was fully hardened at 1450 degrees. Where the original hardness of the two steels was very close, 9 for the one and 10 for the other, the maximum hardness obtainable in the lower carbon steel, 45, is considerably less than that of the higher carbon steel, 60. These then are the values in which we are most interested: the lower critical temperature, the upper critical temperature, the original hardness, and the maximum hardness. Now let's check these findings against a third plain carbon steel with a carbon content between those of the two steels already observed. These micrographs are of an S.A.E. 1031 steel, containing 31/100ths of 1% carbon by weight. Here again, we find a similar pattern in the structural changes under heat treatment. In its unhardened state, this steel consists of perlite and ferrite. At its point of initial hardening, martensite has replaced some of the perlite. At maximum hardness, its structure is wholly martensitic. And these are the comparative values. Lower critical temperature, 1,320 degrees. Upper critical temperature, 1,490 degrees. Original hardness, 10. Maximum hardness, 56. The first thing we can note from these data is that while before heat treatment, plain carbon steels vary only slightly in hardness, there is a wide range in their maximum hardness. And the higher the steel's carbon content, the higher is its maximum hardness. Remaining data for these three steels, we can also project an iron-carbon diagram by plotting their carbon content and their critical temperatures. The 1013 steel has a lower critical temperature, the point of initial hardening, of 1,320 degrees, and an upper critical temperature, the point of complete hardening, of 1,575 degrees. The corresponding points for the 1031 steel are 1,320 and 1,490. For the 1043 steel, 1,320 and 1,450. Now draw a line through the 3 points of initial hardening and another line through the 3 points of complete hardening. The lower line, the lower critical temperature line, indicates that plain carbon steels begin to harden when quenched from about the same temperature, no matter what their carbon content. On the other hand, the upper line, the upper critical temperature line, shows that the lowest quenching temperature necessary to produce full hardening changes with the carbon content. If we carried these tests further with steels of higher carbon content, we would find that up to the point where the two lines meet, the higher the carbon content, the lower the quenching temperature at which full hardness is achieved. Beyond this point, somewhat different conditions prevail, and the higher the carbon content, the greater the heat needed to achieve full hardness. This simple iron-carbon diagram provides basic information necessary to a working knowledge of the hardening of steel by heat treatment.